This is slide number 52 and I am your presenter Asloob Mudassar. Now we have the case in which we have the input in front of the lens as shown in the diagram. So we have three planes, zeta eta plane, xy plane and uv plane. All these planes are parallel to each other. The lens is placed at the xy plane. The input object is placed at the zeta eta plane, and the Fourier plane is the uv plane where we determine the field that is incident on the input object. And you know that the optic axis is along the z axis. This optic axis or the z axis are passing through the center of each object, that is passing through the center of the input object, passing through the center of the lens and passing through the center of the Fourier plane. And you can see that the object is lying at a distance d in front of the lens, and the Fourier plane is lying at the back focal plane of the lens at a distance equal to f. So this is the thin convex lens, and the Fourier plane has been labeled, and the input object has also been labeled, and the optical system indicating input object, thin lens and the Fourier plane are shown. So let's read the description. An input object is placed at a distance d in front of the thin convex lens. The zeta eta plane, the xy plane and the uv plane are all parallel to each other and piercing z axis perpendicularly. The Fourier plane is located at a distance f behind the lens. Input object is thin, and that is it has an amplitude transmittance function represented by Ta of zeta and eta. So Ta of zeta and eta is the amplitude transmittance of this input object. Now the plane wave of amplitude A is incident normally on the input object. For a normally incident input plane wave, we can omit the constant phase factor, so we can only have a factor that is capital A contributing from the plane wave. So dropping the constant phase factor due to the plane wave, the field just after the input object can be written in the following form: U of zeta eta is equal to A multiplying to the amplitude transmittance, which is Ta of zeta and eta. So this equation, which is equation number 35, will give you the field just after the object. The field just before the lens is represented by UL of x comma y, which can be related to the field U of zeta and eta through the Fresnel free space propagation transfer function. So you see that now we have calculated the field just after the input object, which we have labeled as U of zeta and eta, and from this one we have to calculate the field just before the lens, which is UL of x comma y. So you know that the relationship between these two fields is given by, that is UL of x comma y is equal to the inverse Fourier transform between the two functions. One is the Fresnel transfer function, free space transfer function, which we have represented as capital K as a function of fx comma fy, and the other one is the Fourier transform of the field just after the object, which is U of zeta and eta. So this transfer function will make this field U of zeta and eta to propagate by a distance small d. So you know that in the replacement of this capital K, we have introduced its value, which is e to the power minus iota pi lambda d, and you see that here we have inserted d, and this is the distance after which we wanted to calculate the field on the left hand side, which is UL. So e to the power minus iota pi lambda d multiplied by within the brackets fx square plus fy square is the Fresnel free space propagation factor for a distance equal to d. And now you know that on the right hand side we have the field, which is the Fourier transform of the field just after the object, which is U of zeta and eta, as given in equation number 36. And in order to calculate this field, we have to evaluate the Fourier transform, that is the Fourier transform of U of zeta and eta. We have omitted the constant phase factor e to the power iota kd present in the expression of the Fresnel transfer function. So e to the power iota kd, which should be present within the expression of the transfer function, has been omitted because of being constant phase factor. We need to determine the field at the back focal plane of the lens, known as the Fourier plane, which we designate as UF of U comma V. So this is the field we have to ultimately determine. The field just before the lens, which is UL of xy, is connected to the field at the Fourier plane, which is UF of U comma u comma v through the Fraunhofer diffraction pattern. So Fraunhofer diffraction pattern relates the field at the back focal plane of the lens to the field just at the front focal just before the lens, and the formula is this one. So you see that this uf of uv in equation number 37 is the field at the back focal plane of the lens, and that is equal to some phase factors multiplying with the Fourier transform of ul of xy, which is the field just before the lens, and this Fourier transform must be evaluated at the Fourier frequencies, that is at the Fourier plane, which is fu of u over lambda f, and fv is equal to v over lambda f. And you know that this ul of x comma y, we have to insert its value from the previous equation, that is this one from equation number 36. We are going to insert the value of this field into equation number 37, which we have shown in red color. So you know that this operator, which is just operator before the curly bracket, will operate inside. This operator will cancel out the inverse operator within within the bigger curly bracket and outside the smaller curly bracket. So these two will be cancelled out, and we are left with only this phase factor. And of course, the Fourier transform operator should be evaluated at fu and fv with their space variables, which are u over lambda f and v over lambda f. So you see that now we have, you will notice that in the red expression we have the Fourier frequencies, which is fx square plus fy square, which will be replaced by the Fourier frequencies at the Fourier plane, which is fu square plus fv square. So now we need to calculate the Fourier transform of u of zeta and eta, which is the field just before the object, which is the field just after the object. And you know that this ul of x comma y was the field just before the lens in equation number 37. And when we inserted this expression, then the Fourier transform of u of zeta and eta in equation number 38, then u of zeta and eta is just the field just after the object, having an amplitude transmittance equal to Ta. So you see that now we have written this result again, but you know that these two expressions, in the last expression in equation number 38, we have combined these factors, exponential factors. So we have e to the power iota k over 2f, and within the parenthesis we have 1 minus d over f and multiplied by u square plus v square within parenthesis. So we have combined these two phase factors, and now we have the simplified form of the formula in the last step of equation number 38. But you know that we have to calculate the Fourier transform of the field just after the object, which is u of u of zeta and eta. So you see that here in equation number 9 we are going to perform the Fourier transform. So the Fourier transform of the field u of zeta and eta to be evaluated at fu is equal to u over lambda f and fv is equal to v over lambda f is given by the integral in the second row. You know that so double integral from minus infinity to infinity of the field u of zeta and eta, and you know that the rest of the quantities are related with the Fourier integral. So at the end you see that the Fourier integral should be evaluated at f zeta will go to fu and f eta will be replaced by fv. So we have made these changes in the Fourier transform, and you know that we have also substituted the field from the second step u of zeta and eta into the third step by its value, which is a multiplied by the amplitude transmittance of the input object as a function of zeta and eta. So you know that in the last step in equation 39 becomes equal to, by replacing fu and fv by their corresponding values in terms of the space variables, we have double integral from minus infinity to plus infinity a into ta of zeta and eta multiplied by e to the power minus iota 2 pi over lambda f multiplied by u zeta plus v eta. And then you know that the integration is with respect to d zeta and d eta. So you see that we have calculated this Fourier transform, which we shall plug in and in the equation number 38. So 39 will be used in equation number 38, and the result becomes as shown in figure, as shown in equation number 40. So you see that we have we have the field which is UF, the field at the back focal plane of the lens or at the Fourier plane as a function of u and v. On the right hand side you will see that all the quantities are dependent on u and v, and of course the integration is dependent upon the zeta and eta coordinates. So you see that if you set d is equal to 0 in this expression, this will reduces equation number 40 to equation number 26. That is the previous case in which the object was just at the front of the lens. So equation number 26, that is when the input object was located just before the lens. But setting d is equal to f, if you set d is equal to f over here, what will happen? D over f means that this quadratic phase factor, which is based on u square and v square, will be cancelled out from equation number 48, and you know that this quadratic phase factor which is associated with the uv plane will be omitted or will be cancelled out if you set d is equal to f, and you know that this is a very special case. If you want to get rid out this if you want to get rid out of this quadratic phase factor, you have to set d is equal to f. So this is a very special case, and we have mentioned this case over here. Setting d is equal to f makes the quadratic phase factor related to the Fourier plane to disappear, and the field at the back focal plane becomes proportional to the field at the front focal plane of the lens. Now you see that there is another factor which we want to explain over here, and that is the vigneting effect. What is the vigneting effect? Let's read this statement and then we shall explain it with the diagram. If we use a lens with a larger focal length, diffracted wave fronts of the input object which reach the lens aperture may not be fully intercepted by the lens, and a portion of the wave front due to higher special frequencies contained in the input object may be lost. The loss of portions of the input wave front due to finite size of the lens aperture is referred to as the vigneting effect, and this vigneting effect is demonstrated in this figure. So you see that this the object plane has been labeled over here, located at the zeta eta plane, and an incident plane wave front is normally incident on the object. The plane wave fronts are shown in vertical arrows and the arrows show the direction of the plane wave front hitting the input object. And you know that there are diffracted wave fronts at an angle theta diffracted in other directions, which we have labeled at the end with vigneted wave fronts and rays. And you know that this part of this vigneted wave front is intercepted by the lens, and the lens will focus that part of the wave front at its back focal plane, that is at the Fourier plane, which we have marked as the point u comma v. And you know that if we join this point u comma v through the center of the lens, it will meet the object plane at the point zeta and eta. So from the point zeta and eta, the light is passing straight through the lens center to the coordinate uv at the Fourier plane. So you can see that the vigneted wave front is the wave front that has not been captured by the lens, and that has due to the limited size of the lens aperture, and you see that some part of that diffracted wave front has been captured by the lens, whereas the part of the lens which has not been captured by the lens is referred to as the vigneted wave front. And you know that here we have labeled the distance d, that is the object is placed in front of the lens by the distance equal to distance d, and the Fourier plane is located behind the lens at its back focal plane, or at a plane which is at a distance f behind the lens. The rest of the things are very clearly mentioned. So this is the optical system indicating vigneting wave front not contributing at the Fourier plane. So let's read some more things. How to minimize this vigneting effect? Number one, replace the lens with another lens having larger lens aperture but with the same focal length. So if you replace this lens with another lens having the same focal length but with the larger diameter of the lens, you can capture some of the vigneted wave fronts and you can focus them at the UV point. The second point is that bring the input object closer to the lens, in which case the object distance d will be less than f. So bring this object closer to the lens, so that is reduce the distance d. So this object will become closer to the lens, and the wave front will then may be fully captured by this limited size of the aperture. So these are the two possible techniques we can remove or we can minimize the vigneting effect. In this case, the quadratic phase factor will not be eliminated. Equivalently, a lens with the same aperture size but of shorter focal length can be used. So you see that this is the way that we have mentioned in order to minimize the vignetting effect. And you know that this quadratic factor can only be eliminated if you set d is equal to f. But if you set any other value of d which is not equal to f, then of course this quadratic phase factor cannot be eliminated, as explained over here. That is, in this case the quadratic phase factor will not be eliminated. Okay. Vignetting can also be minimized by illuminating the input object with a spherically converging wavefront, but in that case the formula in equation number 40 will not be applicable, because in derivation of this formula we have used a plane wavefront incident on the input object normally. A specific point on the Fourier plane is contributed by a specific diffracted wavefront. When UV scans the Fourier plane, P of x, y would change effectively, though the physical size of the aperture function does not change. For u is equal to 0, v is equal to 0, the effective lens aperture becomes equal to the physical lens aperture. So when u is equal to 0, v is equal to 0, that is when this point uv comes on the Fourier optics plane, that is when u is equal to v is equal to 0, then this point zeta and eta will be located at the optics lens on the object, that is u is equal to 0, v is equal to 0, and zeta will also be eta, and zeta and eta both will be equal to 0 in this case, and the lens aperture pupil function will be lying on the center of the lens also. But you know that if this UV point scans this Fourier plane, then of course the pupil function P of xy will also change its position effectively. So in order to include the pupil function in this expression, you know that in this formula which we have derived over here, but this formula does not involve any pupil function. It means that the object is of infinite size, and of course the lens is also of infinite size in equation number 40. So in order to show a finite size of this one, we have to include the pupil function, but we cannot include the pupil function at its fixed position, that is at p of xy, that is p at x is equal to 0 and y is equal to 0, because that pupil function will also change its location as explained with respect to the point uv. When it scans the Fourier plane, then of course the pupil function will also shift. So we have to include the pupil function in terms of the zeta and eta coordinates, that is as a function of input object. So the integration in equation number 40 is with respect to d zeta and d eta, and therefore we cannot introduce lens pupil function in terms of x, y, that is p of x, y cannot be introduced. We have to represent the lens pupil function in terms of zeta and eta coordinates. If we look back at the input object plane from the Fourier plane, that is u, v, we shall see that the center of the pupil function will be projected at the point zeta and eta. To find the corresponding values of zeta and eta coordinates, we consider the dotted ray in the previous diagram through the center of the lens. So you see that corresponding to this UV point on the Fourier plane, the center of the pupil function will rest on the zeta and eta plane, which is shown on the object plane. We have to find the coordinate of zeta and eta using this geometry, that is the two triangles. Both are making an angle theta with respect to the center of the lens. One has a base equal to d, the other has a base equal to f. So using these two informations in the diagrams, we have found these two expressions. Look at the last expressions only, that is eta plus d over f into v is equal to 0 and zeta plus d over f into u is equal to 0 as in equation number 41. So the pupil function, the lens pupil function p of xy, which is centered at x is equal to 0, y is equal to 0, at the lens plane will now be centered at zeta plus d over f into u is equal to 0, comma eta plus d over f into v is equal to 0 at the object plane, and we can therefore insert p of zeta plus d over f into u, comma eta plus d over f into v within the integral given in equation number 40 to show an explicit dependence of the field u of f as a function of u comma v on the lens aperture. So we are inserting this one in equation number this one in equation number 40. So we are going to insert p-12 function p as a function of zeta and eta coordinates in equation number 40, which we have shown in equation number 42. So you see that you can see that the pupil function has been inserted as a function of zeta and eta, and also as a function of u and v, and there are geometrical parameters d over f and d over f on both the coordinates. So you see that now this provides a full information and also has limited the size of the pupil function. The intensity expression is computed by multiplying the uf by its complex conjugate. So you see that in equation number 43 we have the final result. So the field at its back focal plane is equal to a square over lambda square f square, and the mod square of the integral from going from minus infinity to plus infinity t a of zeta and eta multiplied by the pupil function, and then of course e to the power minus iota 2 pi over lambda f. Within the parentheses we have a u zeta plus v eta, and integration is with respect to zeta and eta. So you see that this is an intensity expression at the back focal plane, and in this case at the Fourier plane of the biconvex lens of focal length f, when a plane wave of amplitude a normally illuminates an object in the transmission mode having amplitude transmittance Ta of zeta and eta located at a distance d in front of the lens. So this is the end of slide number 52.